Okay, problem question on homework.
That's
3.5.
3.7.
3.5 and 3.7.
All three. Alright, so you do 3.5?
Yes, we're doing 3.5.
Solve the problem.
No worries. What 3.5 was good for everybody?
Number 27. Question is, a piece of wire of 10 meters of length is cut into 2 pieces. One piece is bent into a square, and the other is bent to an equilateral triangle. How should the wire be cut to have a manual carrier?
Make my life easier, maybe I want to make this one the triangle and that one the square. And it's an equilateral triangle. Alright, so you have a piece of wire that's 10 meters long. You're going to cut it into 2 pieces. One piece you're going to bend into a triangle, one piece you're going to bend into a square. So I just call the length of the piece I'm going to make for the triangle x, the length, and the remaining is just 10 minus x. So now, this means the triangle will have to look like what?
Wait, Professor. I was confused on the first thing. You know, how can you just make the small part x? Why don't you make the whole thing x?
What point would that serve?
So that you know it's 10 minus x.
No, it's true.
The whole thing is 10.
Oh, the whole thing is 10.
And then I cut off a piece of length x. I don't know what that length is, that's why I call it error. But what's left over would be 10 minus x, whatever that is. I'm going to take the length x, I'm going to turn it into a triangle, an equilateral triangle. So what does each side look like? Huh?
No, it's going to look like x times 10 minus x.
No, each side would be x over 3. It's an equilateral triangle. They all have to have the same side. And the square would look like what?
It's going to be 1 over 4.
10 minus x all over 4 for each piece.
Yeah, 1 over 4, 10 minus x.
So now I want the area function, right? Now, how do I find the area of this triangle?
There's the formula.
Half base times height, right? Gives the area for the triangle. We'd have to figure out the height. It's equilateral, so if I cut the height, this will actually cut the base into 2 equal parts. So this would give me, this would be x over 6, this would be x over 3, and this height, we can actually use Pythagoras' theorem. We'll get a right triangle when we cut it. So we know that x squared over 9 will be equal to, let's call this h. H squared plus x squared over 36. So I know h. X squared over 9 minus x squared over 36. Right? Is x squared 1 minus 1 over 36. What's that? Huh? 3 over 36?
Yeah.
1 over 3, 4.
3 over, no, 3 over 26.
Over 12, right? And so now we can say h is just going to be x over radical 12. You can simplify that a little bit more if you want, but that's basically it. We're running out of space. This means the area of the triangle is 1/2 times the base times the height.
This x over it's x squared. 6 over
6 radical 12, which I can write as what? 2 radical 3. The area for the square is just going to be this times that, right? It's going to be 10 minus x squared over 16. This means that the total area, that A equal total area, then this means A would be equal to this guy plus this guy. And basically this is the objective. So now you just, you want to minimize that and maximize that. So you have to continue. You got it from here?
Yeah.
I would suppose that getting to this point was the hardest part of the problem.
Yeah.
Right after this, you find A prime that equal to 0. And this problem makes me think there are going to be at least 2 critical points where one is going to be a minimum, the other is going to be a maximum.
Oh, yeah.
Because it asks you for both of them. So it seems like
Well, Professor, on this question, right? You could have made either the triangle 10 minus x or the square 10 minus x.
yeah, it doesn't matter. But I know that when I did the triangle, I was going to have to do something like this and sort of Pythagoras' theorem and all sorts of stuff.
Yeah.
I wouldn't want to do it with that guy. Because it looks more complicated, so I made that the triangle simple.
I would not have found that out on this.
But you could have done it the other way, yes, but you get a more complicated formula for
I would have
each.
only found out once I get there. I was like, oh no. And I read it.
Yeah.
Is it okay if you use AB sin C to find the area?
Well, then you'd have to include an angle. That would make the problem more complicated, because now you're going to have to worry about what is this angle here.
You already know that.
60?
It's equal to 60.
I gotta do this problem again.
You can do it that way, sure. What, you mean 1/2 AB sine theta?
Yeah, I do like that, because you don't have to find the height.
Yeah, wouldn't you get the same thing?
Yeah.
Wait, how do you get it? So it's hard to do it. Now you're asking how you did it.
Or, remember when you have a triangle where this is angle A, this is A, B, C. The area of this triangle is given by 1/2 AB sine A. You could use that formula. Here, because we know it's equilateral, we actually know A, right? So for equilateral triangle, you can say A equals 1/2 AB sine of 60 degrees. So in this case, our A and our B are the same thing. So you could say it's 1/2 A, which is x over 3, times B, which is x over 3, times sine of pi over 3. What's sine of pi over 3? Radical 3 over 2. Exactly. And that would work. So this is x squared radical 3 over 36, which is the same as that, right? If you rationalize this, you get that, right? Radical 3 over radical 3. A lot easier. You get that. So, yeah, several ways you can do it. But with either way, I'd rather the triangle has this guy as opposed to that. Yeah, but once you get here, you know, you find the critical points of this. You find the minimum and the maximum. Other questions? Yes, this is true for any triangle. That's also true for any triangle.
So we could have used that.
Yeah. But at the end of the day, you're going to end up with this function that you want to maximize and minimize. Yeah.
What was that?
In 3.5?
Yeah.
What did it say?
This is a rectangular storage container. We can open top.
A rectangular what?
Rectangular storage container.
Okay. Rectangular.
Yeah, and this volume can be cube and it doesn't have any top.
Okay, so no top. Alright.
The volume is 10 meter cube.
We know that the volume is 10 meters cubed.
Yeah.
What else do we know?
The length of this base is twice the width.
The length of the base is twice the width, so if I can make one x and the other 2x, and this could be y or whatever.
And the cost is for the base is $5 and the sides are $3.
The cost of the base is 5,
$5,
and the cost of all the sides,
$3.
3. And I guess we want to minimize costs.
Yeah. This is material for the sides cost $3 per square meter. So is this the whole side or is the only one side?
All of the sides.
All sides, so you have 4 sides.
So all sides included is for $3.
Right.
Okay.
So what is our constraint and objective?
Volume.
Constraint is the volume. We know that the volume must be 10, which is equal to 2x squared y, right? And the objective would be the cost, which I know is the cost of sides plus cost of base per unit area. So the cost of the sides is $3. There are 4 sides. 4 sides times the area of the sides. Will they all have the same length? They actually won't, because one is twice. So it's $3 times, if I take the right side and the left side, the area is x times y. Right, so it's just 2xy plus, if I take the front and the back, that's 2xy times 2, that's 4xy, plus the cost of the base, 2x squared times 5. So this is going to be 6xy times 3, 3 6 is 18xy plus 10x squared. And that would be my cost function. Now, this I want to minimize. So what's the next step? Solve for variable constraint, plug into the objective, right? So I would solve for y. Since y is equal to 5 over x squared, we have that c is actually equal to 18x times 5 over x squared plus 10x squared. This would cancel that. So c is going to be, what's 18 times 5? Huh? Right, and now you minimize that. So you're going to take and this is from WebAssign. It's not, I don't know if there's probably something very similar to homework. They'll change the numbers. So c prime is going to be minus 90 over x squared plus 20x for min c prime equals 0 or undefined. Obviously the undefined case we don't care about because it's undefined when x equals 0, which means we don't even have a box. So this is the only case we care about. And so we just set minus 90 over x squared plus 20x equals 0. And we solve for x. To multiply by x squared. So this means x cubed is equal to 9 over 2. So x is going to be the cube root of 9 over 2. Which for 201 is a typical kind of number.
Yeah.
They always give you something to the fifth root of 69 over 17.
So I solved it, and then when I put in the slot, I
I got it
Right.
wrong because
Now, you could test it if you wanted to in C prime, but I'm sure you see that as the minimum. It would be negative here and positive here. So, y would be equal to, what did they ask us for? The dimensions, or did they ask us for something else?
find the cost.
They actually want the actual cost, which means I don't need to find y then.
Yeah.
So the cost is, right, that's the importance of step 6, to know when you don't have to do extra work, because you know what you're looking for. I already know the cost in only x, so I really don't need the y, right? So I'm not going to waste my time finding it. So it's 90 over this guy plus 10 times 9 over 2 to the 2/3. So I can write this as 90 times 9 over 2 to the minus 1/3, or something like that. That would be the cost. Now, if they had asked you for the dimensions of the box, that would be a completely different thing. We'd have to find the y, and we'd say the length is this, the width is this, the height is this.
It's from what I said. Find the point on the ellipse.
It's getting me to do his web assignment.
It's actually.
You know someone has guts when they ask the professor to cheat for them. What is it?
It's asking for the ellipse, find the point on the ellipse, 4x squared plus y squared.
4x squared plus.
That's the farthest area from point 1.
That's the equation?
Yeah,
You want. Yes, it's an ellipse. You divide through by 4, and you'll see it has the general form.
the farthest area from point 4.
Farthest point from
Yeah, I was gonna ask that.
1, 0. This means you want to maximize the distance function. So let xy be on the ellipse. I want to know the distance between xy and the point 1, 0 will be given by the radical of x minus 1 squared plus y squared, which this guy acts as their constraint actually. I can solve for y squared here and just plug him in here. Or minus 4x squared. That's a horrible looking guy, but it turns out for distances we can sort of cheat a little bit. Yes?
You can change the v.
Notice if we minimize the square of the distance, the distance is also minimized. So in a weird way, you can actually ignore the square root. So take objective to be d equals just x minus 1 squared plus 4 minus 4x squared. Right? Because if you make the guy underneath the square root as small as possible, the whole square root itself will be as small as possible. Right? Because square root is an increasing function. So you can actually just ignore the square root and just use that as your objective. So d prime would be 2x minus 1 minus 8x. For max d, set d prime equals 0. It's never undefined because it's a polynomial. So 2x minus 2 minus 8x equals 0.
Negative 6. 2 equals x plus 4. No,
What?
X plus 3.
What are you talking about? Negative 6x equals 2, right? So x would be
1
minus 1/3. And again, of course, you can test that in D prime to check that that actually gives you maximum. Which, does that actually make sense? You guys remember how to graph ellipses?
Yeah.
So if you have 4x squared plus y squared equals 4, this means that x squared plus y squared over 2 squared equals 1. And so what this ellipse looks like is on the x it goes between 1 and minus 1, on the y it goes between 2 and minus 2. So your ellipse is elongated like that. And we care about this point. Right? So it's the point that's farthest away. It's when your x value is minus 1/3, which means either this point or that point. This will be the farthest distance from it. Right? You'll actually get two answers. Right? Which makes sense. If you did something and you got like x equals 1, then you know something's off, right? Because it's clearly not the farthest away. Come again? Where's the radical, you said? I ignore it. To make my life easier. That's what you get. Because once underneath the square root is this as maximized or minimized, I think I write minimized. We want to maximize. Because I know how the square root function looks, right? It looks like this. Which means the bigger the x value, the bigger radical x actually gets. So I can actually, if all I care about is size, then x and radical x will grow at the same time, or they'll decrease at the same time. So I can just ignore the radical and figure out how this guy is growing and make him as big as possible, and overall the whole thing will be as big as possible. Questions on 3.7?
Please.
What is it?
We'll leave the dock at 2 p.m. We'll travel south.
That one's not like it's going to be here annoying. Okay.
Travels at a speed of 20 kilometers per hour.
20 kilometers per hour.
Yeah, and another boat has been heading east at 15 kilometers per hour, and it reaches the same dock at 30.
And the speed here is
15.
okay. What's the question?
At what time on the boat's close to?
So the distance here is what we care about. Want to minimize E. So what do you think the relationship's going to be? Yeah, distance formula in the form of Pythagoras' theorem. It's a right triangle. So how do we actually set up functions for this thing? I probably do it in terms of time. So I don't know if you want to call these guys something. Call this boat A, call this boat B. So after time t, boat A travels a distance of what? 20t. If t is in, of course, hours. Right? And boat B travels 15t. Okay? So I'm going to try to set up the triangle with those variables now. So if I set this to be d, this guy would be 20t, right? So what would this guy be? Did they tell you the starting distance, how far away it started, or no?
No.
Give you time to.
Huh?
They give you time. Like after.
Yeah, they say at 3 it reaches the point that.
Oh, when time equals 3?
Yeah, because it starts at 2 and at 3.
Oh, I missed that part. Okay, so the journey starts at 2. Start is 2 a.m. p.m.
Yeah.
And B reaches dot at what time? At 3 p.m. Right? Yeah. Right, so they've been traveling for an hour, which means that we know that this distance and in the beginning is 15 kilometers. Which means this guy here, well, the original position was 15, which means the length of this triangle is going to be 15 minus 15t, right?
Elaborate.
Well, the boat is starting here, traveling in that direction, right? We know after time t, it traveled 15t is the distance, right? So if he starts here, at some point t, the distance he traveled is 15t.
Okay.
But the whole distance is 15. So the distance here would just be 15 minus 15t, which means that gives us our constraint where we can find d. Pythagoras' theorem says this is going to be 20d squared is equal to 20t squared plus 15 minus 15t squared. And now we just minimize that in terms of t. That's probably the set I would do. $3.7.
25. I forgot how to do the antiderivative, the particle, but it's x to the 1/2.
It just has x to the 1/2.
Yeah, I don't know, time, parentheses, open parentheses, 6 plus 5x, close parentheses. Yeah, find the antiderivative.
Oh, you want to find the antiderivatives?
Yeah.
They don't really use this notation yet, but I'll just use it. What do you think you have to do to
Yeah, distribute and then take the derivative.
distribute? Right.
Wow.
You were trying to do some
Yeah.
So if you're thinking of doing some sort of product rule for antiderivatives, it turns out one does exist, but that's calc 2. And even in calc 2, this is the way I would do this integral. I wouldn't try anything fancy. I would have done it this way anyway. And then we know the rule, right? That we have x to the n, the x, this gives us what? X to the n plus 1 over n plus 1 plus c, as long as n is not minus 1. The case where n is minus 1, you deal with that in calc 2 because it involves the logarithm. And so this guy would be 6 x to, you add 1 to this, you get 3 over 2. Divided by 3 over 2, which means multiply by 2/3. Plus 5 times 5 over 2 times 2/5 plus c. So this cancels to that 2 times, this is 4x to the 3 over 2 plus 5 cancel 2x to the 5 over 2 plus. Yeah, so just multiply now. Is the way to go here. Let's begin. We're going to go through the appendix and we can go really quickly because everyone read it already. Yes. Now we're going to go to appendix B. 3, where we're going to talk about sigma notation. So, the usual story that people talk about when they're introducing this is that story about Carl Friedrich Gauss, one of the greatest mathematicians of all time. Anyway, of course there are a lot of stories about his prodigiousness when he was a kid. And as legend has it, you know, he was in school one day when he was a kid. I always forget his age, you know, 8, 9, 10, something like that. Anyway, his class was being rowdy, like this class. Right? So the teacher decided to get back there, you know, everyone sit down and shut up, you know. You know what? Keep yourself preoccupied, add all the numbers from 1 to 1,000, right? So like, oh man, or else, you know, everyone's there and you're like, okay, 1 plus 2 is 3. And then, you know, then you add 3, you get 6, and then you add 4, you get 10, and they're all working away. You know, the teacher thinks he got them now, you know, he's sitting back in his chair, relaxes. A couple seconds later, little Freddy slaps the answer on his desk. 500,500 is the answer. Now, how did he do that? As the legend goes, he did this trick. Suppose we want to find, I'm going to call the sum S, and it's all the numbers up to 1,000. The trick that this little guy came up with is he rewrote S, but he actually wrote it backwards. So he said 1,000 here, 999 here, 998 here, 2, 1. And then he decided to add these two. So on this side you have 2S, right? These are just two numbers, so you can add them. What do you notice about the right side? Add these two, you get 1,001 plus, if you add these two, 1,001. You also get 1,001. What if you add these two? 1,001. You also get 1,001. Very interesting. So here you get 1,001 plus 1,001. How many of these guys are there? There are 1,000 of them, because there are 1,000 numbers. This means 2S is actually equal to 1,000 times 1,001, which means that S is equal to 1,000 times 1,001 all over 2. You work that out, 500, 500. In math, it is often very important that we are able to add things very efficiently. And a lot of times we're going to be wanting to add lots of things at the same time, even an infinite number of things. When we get to Calc 3, we're going to like to compute infinite sums because they're going to be very useful for us. So this brings up the notion of summation. How can we formalize something like this? Make it work for our benefit. So there's nothing special about 1,000. I could have picked any number, right? Yeah. Add the first n integers, right? First n positive integers. So you could have done it this way, you know, you start with s equals 1 plus 2 plus n minus 1 plus n, and you just do the same trick he did, right? Turn everything backwards. It turns out that what you're going to get when you add these guys, you're going to get 2s over here, and you're going to have n plus 1, n plus 1, n plus 1, and you're going to have that n times. This means s is equal to n times n plus 1 all over 2, right? So the sum of the first 500 numbers, integers, plug in 500, 500. Sum of the first 50,000, plug in 50,000, 50,000, right? You can add any number of positive integers you want, and all you have to do is that formula. So that's pretty cool. But now we have to worry about things like
No. I just wrote that.
You just write it. We're not forever ago.
It just writes slower.
So actually writing this out all the time gets sort of annoying, you know, and then dot, dot, dot. So we came up with a notation that will compress things for us. It's called sigma notation. Sigma as in the Greek letter sigma, and which is equivalent to S for sum. So for real numbers, call them AM plus 1 to AN, n is less than n. We define, we write this symbol here, goes from m to n, I to b, just adding all these guys together. For example, I could have written this thing by saying, let I go from 1 up to 1,000 of just a formula I, right? Whereas this AI, maybe I should mention that first. That's the definition. Often AI is thought of as a formula or a function of it. I.e., you think of a subscript I as just some function A evaluated at the point I. So you could actually, so now can I get rid of this?
Yeah.
So for example, the sum of the first 1,000 integers I could have written in that very concise way, right? This just means you plug in the numbers into the formula at each given step. So you start with 1, you plug in here, you just get 1, right? Then it moves on to the next guy, 2, then the next guy, 3, and you continue until you get up to the top. So you plug in all values I another parenthetical statement, I is called the index.
Okay, good. And it's coming through for you.
So another example, what if I said I want I goes from 2 to 5 of 3I. What is that equal to? You just plug in this number for I, right? So it's 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. Right? So just 3 times 2 plus 3 plus 4 plus 5. Right? It's just shorthand for all of this. Right? It's just a nice way to write summing a lot of numbers. So now we can write I equals 1 up to n of I. What do you think that's equal to?
Is I times n.
I times 1.
I don't know. 1 and c.
Well, write this out. What is this? If I take I goes from 1 up to n of I, what is that actually saying?
So 1 times I.
Plug in 1 plus plug in 2 plus
Until it gets
plug in 3, and you do that all the way up to n.
So,
I equals 0, I minus I less than n, I plus 4. So you take I 1 by 1.
To the top number
but it's
and
less than
sum
n.
all the terms. Right, but this is just the sum of the first n integers, which we know what that is now.
Wait,
We know how to do this now, right? What was this? N times n plus 1 over 2. Right, so that's a very important formula. You have to know this. Sometimes on finals they give it to you, but I can't guarantee that they will give it to you, so just know it just in case. Other important formulas. You have the sum of the first I squared numbers. Right? Remember, this just means 1 squared plus 2 squared plus 3 squared plus n squared. That also has a formula. N times n plus 1 times 2n plus 1 all over 6. Right, you also have to have memorized. Sum of the first cubed integers. This is just 1 cubed plus 2 cubed plus 3 cubed. It's n cubed. That is actually n times n plus 1 over 2 all squared. Don't really have time to derive these, so just take my word for it. It's actually, they actually prove them in the appendix, so if you care, you can actually just read it. Some important properties. The following are true. If you're doing this to a constant, then the answer is just going to be C times the highest, the maximum index. Right? Where C is a constant.
is I like imaginary number or like
No,
I
it's not an imaginary number. It's just something, it's what we're calling the guy that gets plugged in. Right? So, example here is if I sum 1, right? Where I goes from 1 to n. Remember, you're thinking of this as a function, so when you plug in numbers into a constant, it doesn't change. What you end up doing is just keep adding the constant over and over. And since we're doing this n times, the answer is just 1 times n. Right? The same would be true if I had the number 3. It would just be 3 added to itself n times. So that's 3 times n. So I want to take I from 1 up to 15 of 5. What's the answer? That's going to be 5 times 15. Huh?
You don't divide by 2.
On that formula.
Oh,
This is
C
a
is
constant.
constant. Oh.
N is 15. So it's just C times N. This is one property. It's just adding. If you can write it out and see it. The other property is.
I always want to.
No, I can start from any number. I'm just doing this because it's the easy examples. I can change it to anything. If I have something like AI plus or minus BI, then I can actually distribute sums across, distribute the sigma across the sum.
What about the minus?
Yes, plus or minus. You just follow the sum. So why does this work? Well,
Wait, I equals 2. Oh,
if I'm adding AI plus BI, what would that give me? Well, I plug in I equals 1 plus I equals 2 plus all the way up to I equals n. But addition is commutative, so I can actually regroup these guys. I can add all the a's together first if I wanted to, and then add all b's together. But that's just a shorthand sum of a that goes from 1 to n plus this one is the sum of b dot I goes from n. So I can actually distribute summations across sums. It doesn't work for products. Another thing is, a very important third property is, if you have a constant times the function, you can actually factor that constant out.
So AI is the function?
Yeah, AI is the function. Any guy with I in it is, you think of it as a function. You're going to be plugging in these numbers into it.
So AI and BI are just 2 functions?
Yes, these are just two separate functions. I'm going to give you concrete examples too.
So in this type of question, we have 2 functions?
Yes, you'll have functions. Eventually in chapter 4, we're going to be throwing functions into these guys.
What do you mean 12 functions?
So,
more functions? 3, 4 functions?
yes, there will be many functions, and they would look nasty. Right. You can do that, but now C is a common term, so you can factor that out. But this I can just write as a summation.
So how do you know that you don't divide by some number?
Because I only do it when I have this specific formula. The formulas are very specific. You don't divide by anything unless it tells you.
Oh, I see the pattern when you...
Right. So if there's an I here, that's the answer. If there's an I squared, it's that answer. If there's an I cubed, it's that answer. Anything else? Well, at this point we don't know. We'll just have to work it out along. So let's try to get some stuff done here. How about this one? Compute.
I have a question.
Yes.
So when you use all those together, it's a whole different thing.
You can use all the same. Right, so let's move on. I can use this property and that property together, right? Well, I can use this one where I can distribute the sum. So this is just I from 1 to 100 of 2I cubed minus the sum from 1 to 100 I squared plus the sum from 1 to 100 1. This is by property 2.
I have a question.
Yes.
So what if you don't want 1 to 100? What if you want even numbers? How do you do that? You know what I mean?
The formula, you change the formula, not this. This will always count every integer. If you want that to change, you have to change the formula here. You can actually manipulate a formula so that it always outputs the even numbers. That will come later. Here I can actually factor out the constants. And now we can actually use the formulas that we know, right? This is by how do I sum the first 100 cubes? Yeah, just follow that formula. This is going to be 100 times 101 over 2, and then I square it.
Is it only the power of 1 to 3?
These are the ones we have to know.
Is it 3? Like power of 1 to 3, that's it?
Yes. In Calc 3, in Calc 1, that's all we have to know.
Do we have to memorize that?
Yes. I squared, we have to memorize that formula. It's n times n plus 1 times 2n plus 1 over 6. In this case here, n is 100. So it's 100 times 101 times 200 plus 1 over 6 plus, what's this guy? 1 times 100. And whatever that is. But understand that what you're doing is you're actually adding this formula 100 times. Right? But we know the shortcuts, we don't have to go through the grunt work. We can just use the formula.
Do we have to compute this?
Huh?
Do we have to like go through all that document?
Yes, eventually you'll have to go through all this. Yes. Well, no, you'd actually say.
And now this is when you're yeah.
You have to start from derivatives to learn derivatives. For particle questions, particle problems.
Yeah, for now you're just reversing derivatives. That's how you're doing it.
So you have to know the derivatives. Do you know the derivatives?
Yes. Until we get to chapter 4.
Just learn the antiderivative today.
Okay, how do we find that one?
So we have
Separate.
This is called telescoping sum. Notice that I can't apply any of the formulas I had before because this is 1 over I. It's very different from that. You can't assume the same formula applies. What happens though is you start to plug numbers in to see if you can figure some formula out, right? So you plug in 1, what do you get?
1 over 1 minus 2.
1 minus
over
a half, right?
Yeah.
What if I plug in plus?
Yes. 1 over 2 minus 1 over 3.
Plus, what if I plug in 3?
1 over 3 minus 1 over 4 plus.
Right? And this keeps going, right?
Until
Until, let's say I'm at 98.
1 over 99.
So I have 1 over 98 minus 1 over 99. If I'm at the 99th number, I have 1 over 99 minus 1 over 100, right? This is where it would stop. Now, are you noticing anything happening?
Yes.
Yeah.
And plus 1.
You can cancel everything.
Things are canceling, right? This is what telescoping sum means. It means all the guys, like a lot of the guys in the middle end up killing each other. So this minus half and plus a half, minus the third plus a third, minus a fourth plus a fourth would be the next number, right? This guy is going to be killed by the number on the right here. This 99 is killed by that one. So really at the end of the day, this is just 1 minus 1 over 100. Right, this is called a telescoping sum, so it's just
Justin.
right? Sometimes this will happen. You don't know a formula, so you just start writing stuff out, and you might notice things working out. In Calc 3, this is going to be very important. So remember, for 2 semesters. It's going to come back in Calc 3. And then they're going to be like, you learned this in Calc 1, right? And you're just going to write down the answer. What if I asked you 1 up to n? 1 over I minus 1 over I plus 1. What do you think the answer would be?
There will be 1
1
minus
minus
1
over. No,
plus
1 minus 1 over n.
Right, you can start writing out the thing here. I mean, I could do it. We don't have to do it. But then when you reach like 2 before, you have 1 over your n minus 2, minus 1 over your n minus 1, plus 1 over your n minus 1, minus 1 over n. Plus 1 over n minus 1 over n plus 1. And you notice that the same thing will happen. Everyone in the middle is going to cancel except the first guy and the last guy. It's not always the first guy and the last guy. There could be several guys that survive, but the idea is most of them will cancel out. Right? Here's a definition. Remember how I said sometimes we're going to want to be able to add an infinite number of things? Yeah, that starts now. We won't, that happened way before Calc 3. Here's the definition. The sum from 1 to infinity of AI just means you add forever, right? The strangest thing is sometimes you actually get a finite answer for this, as strange as it might seem. A lot of times you get a finite answer, right? And by definition, we consider this to be the following. This would be the limit as n goes to infinity by sum from 1 up to n of the function, right? So I just think of it as keep adding a term and just keep going, right? So I make n to be the end point, but then I let n go into infinity. So the end point is just running away, right? So.
Why would you get a finite answer?
We're going to show you now an example where we get a finite answer. Like this guy. What if I add an infinite number of terms of this form? Right? So it's 1 minus a half plus a half minus a third plus, and I just keep going. Would I actually get an answer?
No, infinity. But in
Turns
this
out-
case you will because it's not.
In this case, I will. Because this guy, it's not going to be 0. This I think of as the limit as n goes to infinity of the sum from 1 up to n. But I know what this guy is, right? What's that? 1 minus 1 over n plus 1. And as n goes to infinity, what do I get? If I add that, going off to infinity, the answer is going to be 1, as it turns out. So yes, it's possible to add an infinite number of things and get a finite answer, and when it comes down to it, that's what makes antiderivatives work. Behind the scenes, an antiderivative is an infinite sum, and you're taking a limit. So remember the first day of class when I told you, calculus is limits. It's derivative, we know the derivative is a limit. We're going to find out later that the antiderivative is also a limit. In particular, it's the limit of a summation. And something has an antiderivative if this guy is a finite answer, and you can actually get a number for it, right? So that is going to be covered more in chapter 4. For now, you should be able to do all the homework for that. For the appendix.
We're going way too fast.
Yeah.
Yeah.
We haven't finished optimization. We haven't finished antiderivatives.
What?
What are we going to do tomorrow?
Test review.
4.1 maybe.
Yeah, see? I knew it. I knew you were going to say that.
Why can't we do test review?
He's not going to do 4.1, he's just saying.
Why can't we do test review?
Yeah.
Okay. Do you guys know how many classes we have left?
No.
Not a lot.
Okay. How many sections in chapter 4 we have to cover? And we have 2 more tests.
Professor, can you extend the date for web assignment homework?
Oh yeah, we barely have.
What? I just did this wrong as homework for. What are you talking about?
I followed everything.
No, just like 1 or 2 days. That's it.
I'll move into Saturday.
Yeah, because this 3 or 4 days.
Wait, what's moved to Saturday?